In this video, I want to walk through two different examples of problems related to forces in motion where I show you how to develop symbolic expressions for either something like the acceleration of an object or person, the size of the normal force on someone, or the size of the combined frictional forces on someone going down a water slide while increasing speed. Developing symbolic solutions is a really important skill to have when you're taking AP Physics 1, AP Physics 2, or just in college physics. So our first example is going to be about a kiteboarder who's being pulled by a kite, essentially causing tension in the string, and we're going to assume that that tension is up at an angle while they're increasing in speed while moving down just like a level road. So here's the question. Here's how it would sound. It is, what is the size of the acceleration of the kiteboarder? And we're going to solve this symbolically, and the question might say, hey, express your answer only in terms of the tension force, the size of the frictional force, the angle the string makes with the horizontal, the mass of the kiteboarder, and G, the gravitational field strength of the Earth. So we're going to try to find an expression for the size of the acceleration of the kiteboarder. If they're speeding up down the level road, let's first think about the sum of the forces in any direction. Well, if they're increasing in speed to the left, let's say, down the level road, that means the sum of the forces in the x direction must be negative. It can't be zero. Forces can't be balanced, otherwise they wouldn't be speeding up to the left. Well, if they're on a level road, they're not accelerating or changing their velocity in the y direction, so the sum of the forces in the y direction should be zero. And if we want to find an expression for the acceleration, we're going to have to use our equation, which tells us how the acceleration of an object is related to the size of the sum of the forces on that object. That's Newton's second law of motion. And if the acceleration is in the x direction, that means we only need to consider any forces in the x direction. So let's start by just thinking through the forces on the kiteboarder while they're accelerating. There's an angled tension force up and to the left. The ground is pushing up with normal force, the Earth is pulling down with a gravitational force, and we'll assume there's some negligible frictional force to the right. Since they're moving to the left, we'll say friction is off to the right. So this is a symbolic solution for the size of the acceleration. It's equal to the sum of the forces in the x direction divided by the mass. But remember, we can only express our answer in terms of the actual tension force, the frictional force, the angle, the mass, and gravitational field strength. So we need to now expand things in this expression until we only have these symbols in it. So let's look at tension. Well, if tension is at an angle, it's got a horizontal component or an x component and a y component at some angle from the horizontal. That's theta right there that we can use. And so let's expand this. What are the forces or the components of forces adding up together in the x direction? Well, we have the tension force trying to speed them up and the friction force trying to slow them down. So our equation now becomes expanding the sum of the forces in the x direction. We have the x component of tension plus the frictional force. And remember, the arrows over the symbols here remind us that these have a size and a direction. And we're just going to keep them over there to remind us that whatever we plug in for the tension force in the x direction or the frictional force, whether it's a symbol or a number, we'll have to decide what the sign actually is. Well, we can't use the x component of tension in our answer. We have to use the actual force of tension. So how is the x component of tension related to the actual force of tension at an angle? Well, we've got our right triangle here. So let's come up with an expression for how tension and the x component are related, also including the angle. Well, to do that, we're going to have to use the cosine equation. All right, the cosine of an angle is equal to the length of the adjacent side, which is the x component of tension, divided by the hypotenuse, which is the actual tension force. So let's rearrange this and solve for the x component of tension. To do so, we just multiply each side by the force of tension. So the force of tension cancels out on the right side and it ends up on the left side. So we get that the x component of tension is equivalent to the actual tension force, Ft, multiplied by the cosine of the angle that the tension makes with the horizontal. And Ft and theta, those are things we can include. So let's substitute this right here in for the force of tension in the x direction. Okay, that's our next step. So instead of Ftx, we just have Ft cosine of theta, because that's the size of the x component of tension. And once we start substituting in symbols, in a symbolic solution, we're assuming that anything you plug in here is positive. So we would plug in a positive value for the force of tension, a positive value for friction, but we have to decide what the sign of that expression is. We know that the x component of tension is pointed in to the left. That's the negative horizontal direction. So we have to put a negative sign in front of the size of the x component of tension. And then what about friction? Like, we can use friction in our final expression, so we don't have to substitute anything in for it, but let's decide what the sign is. We see that in our force diagram, friction is pointed to the right. That is our positive horizontal direction. So we're adding some size of friction, adding F sub F. And that's all divided by the mass. And so our Newton's second law expanded is the acceleration of the kiteboarder is equal to negative Ft cosine theta plus the size of the frictional force divided by the mass. And if we check up here, all of those symbols, they're fair game. We can have those in our final expression. So our answer to the question of what's the size of the acceleration of the kiteboarder is this expression. It's a symbolic answer. Now, if we wanted to find a quantitative answer, like, you'd have to know the size of tension, let's say, is 800 newtons. The size of the frictional force would be 200 newtons in size. We could give an angle of 60 degrees from the horizontal, and we'd have to know what the mass was. Well, if we had these values, we could use our symbolic answer to actually get a quantitative answer. So just to show you what that looks like, we take our symbolic answer, our solution, we plug in the tension force, the angle, the size of the combined frictional forces, keeping in mind the signs in our expression we found, divided by the mass, and you'd end up getting the sum of the forces on the kiteboarder is negative 200 newtons. There's 200 newtons more to the left than the right. We divide by the mass of 100 kilograms, and you'd end up getting an acceleration of negative 2 meters per second per second. So when you're solving physics problems, sometimes you'll be asked to solve quantitatively, that you're going to get a number and a unit, or you find a symbolic expression and you can only include symbols. The problem will specify which symbols you'll be able to use for your final expression. So let's keep looking at this example and now think through, how can we develop a symbolic expression for the size of the normal force? So what is the magnitude of the normal force pushing up on the bottom of the board? And now we're going to express our answers in terms of just tension, theta, m for mass, and g for the gravitational field strength. Well, we already talked about the forces in the y direction. Like, there is no acceleration, so we know the sum of the forces in the y direction must be 0. So let's write out the net force equation for the y direction. Like, what forces or components of forces are adding together that sum to 0? Well, we have the y component of tension that's pulling up. We have the normal force that's pushing up, and we have the gravitational force that's pulling down, and they all have a size and a sign, right? So we have our little arrows over there to remind us to put in the sign before we're done. When we add all of those up, because there's no acceleration in the y direction, they're not speeding up or slowing down vertically, all those things must add to 0. So we have an equation right here. Let's substitute things in here that we're allowed to, and then rearrange and solve for the normal force. Okay? So let's first decide what the signs are. The force of tension in the y direction, that's in the positive y direction, so this would be a positive symbol. The normal force is pointed up, so that's also going to be positive. But gravity is pulling down, so we're going to have to subtract the size of the gravitational force, so it's minus Fg. So you always write out the net force equation with the vector notation, reminding us that each has a size and a sign. And then to get your symbolic expression, first decide what the signs are. Then we start substituting things in and solving for what we're finding an expression for, which in this case is the normal force. So let's first rearrange our net force equation to solve for the normal force. So we get the normal force is equal to something. Well, let's subtract the y component of tension and add the force of gravity to the left side, which means we're going to add Fg to the right side, and then subtract the y component also from the right side, right? Whatever you do to the left side, you do to the right side. So rearranging this for the normal force, we get the normal force is equal to the size of the gravitational force minus the size of the tension force. Now that we have this arranged for the normal force, we just need to make sure what's on the right side only includes the allowed symbols in the problem statement. So we need to replace the force of gravity with an expression which represents the size of gravity, and Fty with something that represents the size of the y component of tension. Well, let's go back to some of the equations that we've already talked about. We have a general equation for the size of the force of gravity on any object, right? It's equal to m times g, the mass of the object, times the gravitational field strength of the Earth. And we can use m and g, so just use mg in place of the force of gravity. And then the y component of tension, just like we did with the x component, let's use our right triangle and find an expression for the opposite side of our triangle, because we know the hypotenuse, that's tension, and we can use that. And we know an angle, and we can use theta. So if we use the sine equation and solve for the y component of tension, the opposite side of our right triangle, we get that the size of the y component of tension is just equal to the tension force times the sine of that angle. So let's plug in mg for fg and ft sine theta for the size of the y component. So we get our final expression for the size or the magnitude of the normal force pushing up on the kiteboarder is just equal to mg minus ft sine theta. And this is our symbolic expression or answer for the size of the normal force. If we went back and used all the same numbers, the given mass, the size of tension, the angle, we could plug those values in and we'd get a quantitative answer. In this case, it would be 307 newtons. For our second and last example in this video, we're going to talk through finding a symbolic solution for somebody moving down a water slide with some amount of frictional force, but it's not enough to keep them from speeding up down the incline. And we've already talked about forces on inclines quite a bit, how to think about it conceptually, rotating the coordinate systems and why we do that, and how to find things quantitatively. So this is not going to go into detail about that. If you want to know more about that, I'm going to include some videos in the description which talk about conceptual force diagrams and quantitative force diagrams on inclines. So just to set up the problem and give context, we need to look at the force diagram. The rider's feeling a pull down from gravity. The surface of the slide is pushing up with a normal force perpendicular to the surface in our rotated y direction, and the person is sliding down parallel to the ramp, so friction is pushing back up parallel to the ramp in the other direction. Since we rotate our coordinate system where the x direction is parallel to the surface and the y direction is perpendicular, we have to think about breaking up gravity into its x and y components. The downward gravitational force has a component parallel to the ramp we call FGX, or the x component of gravity, and it also has a part or a component that is perpendicular to the ramp, which we call the y component. And the angle of the ramp, we talked about this before, is the same angle that gravity makes with the y component, the perpendicular direction. So now that we know that, let's get to our problem. So the problem reads, if a person's acceleration down the theta degree incline, we're solving this symbolically, so we're not giving numbers, we're just giving symbols, so it makes an angle of theta degrees. If the acceleration is represented by A, how large are the combined frictional forces? It says express your answer symbolically in terms of theta, the mass of the rider, the value of the acceleration A, and the Earth's gravitational field strength. So looking at our component force diagram, we have the normal force and the y components of gravity. They cancel each other out. There's no acceleration in the y direction. But in the x direction, we're assuming, well, it says there is an acceleration. So they're not sliding down at a constant velocity. We have the x component of gravity trying to speed them up and friction trying to slow them down. But because they have an acceleration, they're increasing in speed in the positive x direction. We know that the x component of gravity has to be bigger than the frictional force. So if we want to develop a symbolic expression for friction, at this point in the class, we don't have an equation that allows us to calculate the size of friction for different situations. But think about what we're given. We're given an acceleration, and we know other things about the forces the rider feels. So let's start with the same equation we started with in our last example, Newton's second law of motion, because this equation tells us how the acceleration of an object is related to the size of the sum of the forces on that object and the mass of that object. So let's just start substituting in things in this equation with the allowed symbols or variables, and then rearrange this and solve for the force of friction. So we're talking about the acceleration in the rotated x direction, so when we plug in things for the sum of the forces, we only need to include any forces or components of forces in the x direction, because all the y forces or components, they cancel each other out. So in the x direction, we have the x component of gravity being added to the frictional force. And we're leaving the little arrows over there to remind us that we're going to have to first put in positive and negative signs once we get things for the size of those forces. And we're dividing by the mass. So let's first do the x component of gravity. So if we draw a right triangle showing the force of gravity pulling straight down, and we have the y component perpendicular and the x component in the parallel, or what we're calling the x direction, we've got our right triangle. Remember, the angle of the incline will always be the angle between gravity and the y component once we draw a right triangle properly. So we need to get an expression for the size of the x component of gravity, which is the opposite side of a right triangle. So we'd end up using the sine equation. The sine of theta is equal to the opposite side, fgx, divided by the hypotenuse, which is fg. Well, we know the force of gravity is equivalent to something's mass times the gravitational field strength, so our hypotenuse is just m times g. And if we're using the sine equation to find the length of the opposite side, solving it algebraically, if you work it out, you get that the opposite side, which is the x component of gravity, is just equal to the hypotenuse, which is mg, times the sine of the angle. So mg sine theta represents the size of the x component of gravity. How much of gravity is trying to speed up the rider down the water slide? So we can plug in mg sine theta for that. Not that we need it for this problem, but if we wanted to know the size of the y component, that's the adjacent side, and that would end up just being the hypotenuse times the cosine of theta, or mg cosine theta. So if you wanted to know the size of the normal force, hey, that's the same size as the y component. That would be equal to mg cosine theta. But let's get back to the problem at hand. Plugging in things that we can plug in, we have mg sine theta for the size of the x component of gravity, and that's pulling to the right, or the positive x direction, so that's positive mg sine theta. And the force of friction is in the negative x direction, so we're going to subtract whatever the size of friction is. So it's minus f sub f. Now let's think about the acceleration. We have a symbol which represents the size of the acceleration, which is a, and it's speeding up in the positive x direction, so we'd plug in a positive a there. If they were speeding up in the negative x direction, we'd have to plug in a negative a. And m is just m, we can use m right here. So now we have an expression that has all the allowed symbols in there, a, m, g, theta, and m, except for the force of friction. Well, we're not done yet, because remember, we're trying to find an expression for the size of the combined frictional forces. So we need to get the force of friction equals something. We need to rearrange this algebraically so the force of friction is all by itself on one side of the equal sign. Okay, so the first step will be, let's get m out of the denominator on the right side. So we're going to multiply the right side by m and multiply the left side by m. So m will cancel out on the right side, and we get this. On the left side, it's mass times acceleration, or m times a, equals all this, mg sine theta minus the frictional force. Now I'm going to add the frictional force to both sides of the equation. So if we add the force of friction here, it cancels out, which means we're going to add the force of friction right there. So on the left side, we get the force of friction plus the mass times the acceleration is equal to the mass times the gravitational field strength times the sine of the angle. And we're almost there. All we need to do is now subtract m times a from the left side and from the right side. And so we get, on the left side, just the force of friction is equal to mg sine theta minus m times a. This right here, let's just double check. Our expression for the size of the frictional force only includes, does it include just theta, m, a, and g? Yeah, m, g, theta, and a. So this is the final expression for the size of the combined frictional forces using only symbols that you're allowed to in the problem statement. Of course, you could solve the same problem quantitatively, except you'd have to be given a specific angle for the incline, a specific acceleration the rider had, and the mass of the rider. So you could go through the same process. You'd use Newton's second law, and you'd realize that, hey, in the x direction, we've got the x component of gravity and the frictional force. And so if you ended up making your right triangle and plugging in for a mass of 80 kilograms, the rider would have a gravitational force of 800 newtons. Remember, the angle of the incline is the same angle between gravity and the y component. If you actually solve for the opposite side of that right triangle to figure out how much of gravity is in the x or parallel direction, it'd be 325 newtons. And they'd say the acceleration was some value, so you'd plug in acceleration of 2 meters per second, and you plug in the mass of given that was 80 kilograms, and then you just have an equation with one unknown, and you could solve for the size and direction of the frictional force. So if you solve this algebraically, you'd end up getting, if you had these specific values, that the force of friction is equal to negative 165 newtons.